College Algebra folks, back here with another quick set of examples here looking at 4.6 material where we are solving polynomial and rational inequalities. And here we have our first example where we are asked to solve this following polynomial inequality. And if we go back to the notes and the process involved there, this process does begin by considering solving the corresponding equation for this result. So in order to begin solving this inequality, what we're going to do is we're going to solve this equation, the equation that we could form by replacing that inequality symbol with an equal sign. Right? Now what we do notice is this is a polynomial, but more specifically it's a quadratic. We have a highest degree of 2 here. So to begin solving this equation, this quadratic equation, we might try factoring. And I do believe this one factors. We can get a factor of x minus 3 and a factor of x plus 2 will work. So x minus 3 times x plus 2 will equal 0. And that does mean x minus 3 would equal 0 or x plus 2 would equal 0 if we apply the zero product property. Or that x would equal 3 or x would equal negative 2 in value. Now once we find these two solutions, right, in terms of finding the inequality, this is where we equal the value of 0. We're going to be interested in where we're greater than the value of 0. So one of the ways we go about determining that with a polynomial is we are going to put our two solutions on the number line. That being the solution negative 2 and 3. Right? And we know that we're not allowed to equal these values as a solution. We're not going to allow it to be here, and we're not going to allow it to be here. Right? We're going to either have to be greater than 0 in this case, right? But we're not allowed to equal 0 in this case. So these are the locations of x where we equal 0. We're not allowed to be there. In terms of where are we bigger than 0, or even if we were concerned with the case for being less than 0, that would occur around these values. So the way we go about determining where that occurs at is we pick some test numbers. We pick a test number down here that's smaller than negative 2. Maybe we pick negative 3 as a test number. We pick a number between negative 2 and 3. Maybe we pick 0 as a test number. And we have to pick a number bigger than 3 out here. Maybe we pick 4 as a test number. And what we do is we have to go off and test those values inside of our function. Right? We're going to want to plug in negative 3, 0, and 4 into our function and see what occurs here. Now if I plug in negative 3 into my function, this being my function up here, f of x equals x squared minus x minus 6, right? When negative 3 goes in there, we could run it through either one of these lines. Actually, I like running it through the factored form here, because we can see that negative 3 minus 3 is negative 6, which is going to be times by negative 3 plus 2, which is negative 1, and that equals positive 6 in value. And the big thing we're going to compare that back to is this value greater than 0, or 0 itself. Is that 6 bigger than 0? That is true, right? So what we do know is this negative 3 must lie out here in a region where we're going to find a solution to our inequality. All right? 0, if we test 0, we plug in 0 here and 0 here. It's going to be 0 minus 3 is negative 3. 0 plus 2 is positive 2, and we do see that that gives us a negative 6 in value. If I compare that negative 6 to 0, it is certainly not bigger than 0. It is less than 0. So that is not a number that falls in our intervals for solutions. Whereas for the value of 4, if we test that, that'll be 4 minus 3, that's 1. 4 plus 2, that is 6. 1 times 6 equals 6, and again, that is bigger than 0. So this number 4 tests, and this number negative 3 tests when comparing their output from the function f to 0. They are cases where we see greater than 0 behavior. So not only down here do we have solutions, but out here we're going to find solutions. Right? So this is going to illustrate our solution set, and from that we want to put this into interval notation So this starts down here at negative infinity, continues up through the value in -2. We do not include either of those values. That is unioned with the interval starting at 3 and continuing off to infinity. All right, this becomes my solution set, like expressed in terms of interval notation. All right. Keep in mind also, folks, that you also have your calculator to help you check some of these skills. All right. If we were to go underneath y equals and plug in this function, x squared minus x minus 6, and we were to just look at its graph, all right, here's the picture that we're looking for. All right, that does describe this function seen here. And notice where it equals 0 is at these values of -2 and 3. All right, those are what we found for solutions to that inequality, or I should say to the equality of, for the case where it equals 0. So if we're interested in where are we bigger than 0, that is where we're above the x-axis in the graph. And we're above the x-axis out here, which corresponds to, if we're out here, that corresponds to being at this location of 2 and going down towards negative infinity, right? This here starts at -2 and heads down to negative infinity. Whereas we also see we're bigger than 0 out here, which begins at 3 and doesn't include it and heads out towards positive infinity. Right? We have these two illustrated, we have this illustrated function where we're actually interested in that function being bigger than the value of 0, being above the x-axis. Right? And our illustration on our calculator shows us that solution, right? And confirms the solution that we found here using the algebra. All right, so that's our first example. I'll be back here with another short example in a moment. Hey there, college algebra folks. Another quick example here of solving a polynomial inequality. And what you will notice here is we have something that looks a little like a polynomial. It's not quite a polynomial in its format yet. What we would perhaps consider doing to make this look a little more like a polynomial is to begin with, right, treating it a little like an equation, right? So as suggested by the notes, right, when solving these polynomial inequalities, you want to treat the inequality to begin with like an equation. So here we build this equation, 2x cubed minus x squared equal to 5x. Where with this equation, I'm able to subtract 5x from both sides and prepare the equation 2x cubed minus x squared minus 5x equal to 0. Oh, and let's be careful there. That is 2x cubed minus x squared, right? Minus 5x equal to 0. And what we have here on the left-hand side is our polynomial, right? We might think of that as being our function f of x here. And what this equation is implying is that we are, to begin with, interested in when does it equal the value of 0. In terms of when it equals the value of 0, we understand with a polynomial to determine that we do want to consider factoring this polynomial. Now you'll notice in this case this polynomial does factor rather nicely, right? When it comes to time for factoring this polynomial, you'll notice that there is first of all, a common factor of x found in each of these terms. So if I factor that x out, I will be left with 2x squared minus x minus 5 inside the parentheses, all set equal to 0. We're now inside this group. I have a quadratic where I might attempt to factor that quadratic further. Now, if we attempt to factor, we do know the first two terms in each factor have to be 2x and x. Those are the only two things I can have that multiply together to give me 2x squared. Where now I want to think about values that multiply to give me -5, and there's only, what, 5 and 1, that when I arrange those here, right, I can get -1, right, in that calculation. Now, for 5 and 1, 5 here and 1 here, this will give us 5x, and this will give us 2x. That'll give us to 7x and 2x. That is not -x. And if I try to move the 5 here and the 1 here, this is going to be 1x and this is going to be 10x, which will take me either to 11x or 9x, depending upon how I arrange the signs. So this quadratic here does not factor too nicely. All right. In fact, what we may have to do here with that quadratic, right, is actually considering some other methods for solving this, right? We do know that x equals 0. This does imply that x equal to 0 is one solution to this equation. As for the other two, they're going to come from working with this quantity here. Now, a little quad formula might be helpful. If I take this and apply a little quad formula to it, we know x is going to be equal to the opposite of b. b is -1, so that's 1, plus or minus the square root of what's going to be b squared. Now, b squared is 1, minus 4 times this value of a, which is 2, times this value of c, which is -5, all divided by 2 times a. Now, a again is the value of 2. And if I solve this out, I will find this is 1 plus or minus the square root of, and underneath here we have 1 minus this result here. Now, this result here you'll see is -40, or if we combine the negative here with this negative, that would become plus 40. 4 times 5 is 20, times 2 is 40. Added to 1 is actually the result of 41, all divided by 4. All right. In terms of my other solutions for x, we also find x is equal to 1 plus or minus the square root of 41 fourths. All right. So if we consider these values along a number line, right in the middle of our number line would be the value of 0 for x. And then out here on our number line at these other locations, we would have 1 plus the square root of 41 over 4, which we notice would be positive. The square root of 41 is somewhere between 6 and 7. When added to 1, will become somewhere between 7 and 8. And when divided by 4, will be somewhere between 1 and 2 in value. So out here at perhaps, let's do it this way. Let's just make one tick mark. Out here at this location here, we have the value of 1 plus the square root of 41 divided by 4. Whereas the minus situation, right, this is 1 minus the square root of 41. Again, square root of 41 is somewhere between 6 and 7. So if we take that away from 1, we're going to have somewhere between -5 and -6 in value. Where when we divide that -5 or -6 in value by 4, you will end up with a negative result that would be found over here on the left-hand side of 0. This would be at 1 minus the root 41 divided by 4. All right. Again, this is pretty close to between 1 and 2. This is pretty close to between also the values of -1 and -2 in value. All right. Just using a little bit of approximation technique, knowing that the square root of 41 is somewhere between 6 and 7. And as you recall, what we need to do is test these values with some test numbers here, right? We might come up here. Well, I think we could fit our table in down here. If I fold this up, right, to begin making my table. I might put my table down here for x and f of x, and I need to test numbers that lie between these bounds on this interval. We understand these are locations where we equal 0. So we're not going to actually be there, because we're going to be interested in being less than or greater than the 0 in value. And if we start to pick some test numbers, like I said, this is somewhere between -1 and -2. This is somewhere between +1 and +2. It's certainly not the value of -1 or the value of negative or +1. So some good test numbers we might be able to pick would be the values -1 and 1. I certainly am going to want to maybe test those values. And then again, because I said this is somewhere between 1 and 2, and this is somewhere between -1 and -2, if we go to pick test numbers outside of those bounds, we could get away with perhaps using 3 out here, and maybe the value of -3 down here. So we want to maybe test -3 and 3. Keep in mind what we are testing them in is this equation right here. Right? This quantity, right? 2x cubed minus x minus 5. And, you know, that algebra, well, sorry, minus x squared minus 5x. That algebra could be a little heavy, right? Doing that arithmetic there. So one way that we could approach this is actually on our calculator to do this test numbers. This will help eliminate some error. If I put the function actually into my calculator, right? And I go over to my table, actually my table settings, let me change those back to ask here, and go over to my table. I can now test -1, 1, -3, and 3 rather quickly. -1 is 2, 1 produces -4, -3 produces -48, and 3 produces the value of 30. And what I am interested in, folks, is where are these values now bigger than 0, right? And what we notice is that case is a case where we are bigger than 0, whereas here we are not. That is not bigger than 0. Neither is this. That is not where we're bigger than 0, but out here at +3, we are certainly bigger than 0. Where we find ourselves bigger than 0, right? Because notice what we've done here is by treating this like an equation, we have found these boundaries. What we really are interested in is when is this bigger than 0, right? If we go, well, let's be careful there. Less than, we're less than 0. We're actually interested in when are we less than 0 in this case. So let me reverse this. This is, get this backwards down here, right? -1, 1, -3, and 3, these are discarded because we are not less than 0 there, but it's going to be the regions where we see 1 and -3 in value as our x values. Those test numbers produce results that are less than 0, and again, it's really less than 0 that we're interested in our inequality. So what test regions, or what intervals does the 1 lie in? Well, it lies here between these two bounds. And what region does -3 lie in? It lies in this region out here below this bound here, all the way down to -infinity. So in terms of our solution to this inequality goes from -infinity up to this quantity 1 minus the root 41 divided by 4, and is unioned with the quantity that starts at 0 and goes up to 1 plus the root 41 divided by 4. Right? This becomes my solution in interval notation here, folks. Right? So again, that's more solving inequalities. In this case, we were solving this polynomial here in this case, right? The 2x cubed minus x squared less than 5x. Again, you want to begin by treating it like an equation. That is how you're going to find the boundaries on this interval. Once you find your boundaries on this interval, right, you're going to test numbers between those bounds, and we see that happening down here in the table. A really quick way to test your numbers without error is to put it all into your calculator, right? But once we have our test numbers in our calculator, we are looking for, again, if we go back to converting this back to the inequality where things are less than, right? This function is less than the value of 0. And in fact, we could even begin to look at the graph here, We'll see some of this answer is confirmed. Here's our graph. Again, we should see our x-intercepts, if I was just to zoom in slightly here. Oh, apparently I zoomed out. Oh, I did zoom out. Let's zoom in one more level here. All right, there we go. That's kind of a nice illustration of what we saw. We can see our zeros, which should be at 0. This number is somewhere between -1 and -2, and this number out here is somewhere between +1 and +2. All right? That is where our function equals the value of 0. But what we're interested in is where is it less than the value of 0, coming from our inequality. All right? Where it's less than 0 is down below the x-axis. Here, for all the values to the left of this location is where we're less than 0. That was this location on our number line, down to -infinity. And where we're also less than 0 is between these locations on our number line. Down here is where we're less than 0, between 0 and this bound where we equal 0. That was this interval right here, folks. So our calculator does confirm our results for us. All right? So another quick example on solving inequalities, polynomial inequalities in this case, folks. Hey there, College Algebra, back with one more quick example over solving polynomial inequality here. As we had noted in the other two problems, as we start these, we do want to treat them a bit like an equation. I know some of you may be having difficulties getting over to that equation. One thing I will point out is we derive the equation from this statement. We do, in a sense, just want to make it equal to 0, and we can do that a couple of different ways. We can either subtract the 6 and add 4x squared to both sides, which would move these terms on the right to the left, or we can subtract an x cubed and subtract an x, which is going to move these terms from the left over to the right. When you're adding and subtracting those terms from one side to the other, it is not going to change the direction of your sign, right? When I subtract the 6, right, and I add the 4x squared from the left to the right, or from the right to the left, right, to move it from the right over to this left-hand side, it does not change the direction of this inequality sign whatsoever. All right? So if we think of that now as an equation, and I go ahead and rearrange this into a form that resembles a bit more of an equation, we can think of this quantity here on our left-hand side as being our polynomial here. Oh, and I should have a cube there. All right? Where we now want to consider where does this equal 0 and where we're going to find this equaling 0, right? Approaching it as an equation to begin with to find those boundaries along my number line, right? And we notice we are allowed to equal 0 in this case, so to find the first set of answers where we equal 0 in this case, we're going to have to factor this quantity. Now, I will tell you, we could look at a little bit of grouping here, but grouping is not going to work. If I factor out an x squared here, I will have an x plus 4, but this last factor is not in that form, x plus 4. And to obtain that form would be a little difficult back here. All right? So instead what I have to do is use a little polynomial technique. I may have to list out my potential rational zeros here. If I think about my p over my q values, my list of potentials, right? All my p's are going to be the factors of -6, and all my q's will be the factor of 1. Q, being limited in its set, just being the values of 1, essentially p's over q's, my list of potentials are just the factors of 6. So that would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. To begin with, those would be my potential zeros. Now keep in mind, test those, we are just going to plug those into our function here. And as we've seen, the easiest way to do that is on our calculator. If we go back underneath our y equals menu, clear this out, and put in our polynomial x cubed plus 4x squared plus x minus 6. And we go over to our table now. Let's go ahead and clear out this table. We start to test those numbers. We might test 1. Well, 1 right away we see is a 0. All right. In terms of some zeros, x equal to 1 is a 0. Right? If we look for a couple others, right, maybe we test all of them on the list real quick, we actually find x equals -2 is a 0 also. Right? If we test 2, test 3, -3, oh, look, we find x equals -3 is a 0. And because we're dealing with a degree of 3, we're expecting at most 3 zeros, and we have just found them here using our calculator to test out for those zeros, right? What that means is that when I think about this polynomial over here and its factors, using the factor theorem, that would factor in x minus 1 times x plus 2 times x plus 6 in value. And if all that equals 0, then that means along my number line, I'm going to have, this is 0, I am going to have this boundary at 1, maybe right here. I'm going to have this boundary at -2, one of my zeros, which might be right here. And then I'm going to have this boundary at -3. You can see I had to correct that factor there. So this would be -3. This is where I'm allowed to equal 0, is at those 3 locations. And because my inequality allows me to equal, I'm going to have solid dots in those locations. Where now I want to test some numbers around those values, right? Again, testing our numbers happens real nice within our table here. All right? I might test this 0. I might come out here and test 2. In between -2 and -3, maybe I have to test -2.5, which would be -5 halves. And then out here beyond -3, maybe I test a -4. And I already have these in my, I already have this function in my calculator here, right? If I go up there and delete out these results and consider testing these others, if I test 0, that is -6. If I test 2, I get 20. If I test -5 halves, I get, that's 0.875. And if I test -4, I get -10 in value. Where you'll notice again what I'm interested in the inequality here is being less than the value of 0. Well, here we're less than 0, and out here is where we're less than 0. Here is where we're bigger than 0 in value. These are not values that lie in our intervals of solutions, but these are 0 and -4 in value. All right. Well, 0 is a test number in this interval, and -4 is a test number out here in this interval. All right. So in the end, our solution runs from -infinity up to -3. We do include the 3 because 3 can be equal to 0 in our solution, right? Unioned with this interval that runs between -2, and we can include 2 because we can equal 0 in our solution here, up through this other boundary at 1, where we can include 1, again, because we can equal 1 up here in our solution. All right? So, folks, again, this is solving polynomial inequalities. All right? It is going to require you to treat it a bit like an equation and to think about what would be your solutions for the equation. That's where you're going to find the boundaries between where it's less than and greater than 0. And then once you know the boundaries between where you're less than and greater than 0, and you can notice here we used a little rational zeros theorem and our remainder and factor theorem here to come up with this form. Once we have those boundaries, we can pick some test numbers within those bounds and test those out for being less than or greater than 0, depending upon what our problem is looking for. And as I've illustrated on the calculator, our calculator is really powerful in getting us through these problems quickly, right? I use the calculator to test these test numbers, as well as I use the calculator to test over my potential zeros here in my problem, right? So, again, folks, this is solving polynomial inequalities. I'll be back to look at a couple of cases for solving rationals, right? See you then. Hey there, college algebra folks, back with another example here, working through some 4-6 material where we're solving polynomial and rational inequalities, and we have a couple of examples here where I want to work through solving some rational inequalities for us. If we notice here in part A, we do have inequality, right, involving a rational statement. That 1 over x minus 3 is a rational statement. All right. The way we begin with this problem, as we did with polynomials, is we are going to think of it a little like an equation to begin with, right? And think of it being equal to, right, what we have here on the right-hand side, the value is 0. What we might think of having here is we have the case where f of x equal to 1 over x minus 3 is equal to the value of 0. And this here is our polynomial function. Or, sorry, our rational function, right? F of x equals 1 over x minus 3, right? And we do want to consider solving this equation, right? Or thinking about what would be the, perhaps, graph of this rational function, right? One thing we will notice about this rational function, and this was brought up in the notes over this section, is when you go to solve them, right, and we set it equal to this equation, one of the things you have to keep in mind with respect to your equation here in solving the equation is that you're going to have domain concerns, right? If we take note in this case, there is a domain concern. X minus 3 cannot equal the value of 0, which means x is not allowed to be the value of 3 in our solution, right? Wherever we happen to equal 0 at, or be less than 0 at, x cannot be 3 in that interval. So here along our number line, if this is 0 and this is the value of 3, we are not allowed to be there at that domain concern. Right? As for then, when does this rational quantity, 1 over x minus 3, equal 0? Well, that's when this numerator is 0. Now, one thing you'll notice is that numerator is the value of 1, and it can never be 0 in value. So if the numerator here can never be 0 in value, there is no value of x that will cause this to actually equal 0, right? What we might say here, this never occurs, right? This is actually never equal to the value of 0. So what we're left with is just this number line with this one little domain concern on it here, happening at the value of 3. With our domain concerns and with our solutions plotted on this number line, what we do is we use a couple of test numbers and we check again behavior of this quantity 1 over x minus 3. We're now interested in when is it going to be less than or equal to the value of 0. So I might test the number as 0. 0's out here. This is a nice test number, and maybe I'll choose the test number of 4. All right? You'll notice if I plug 0 in here, that would be 1 over negative 3, or negative 1/3 in value. Whereas if I plug 4 into this, that would be 1 over 4 minus 3, or 1 over 1 in value, which equals 1. All right? And we're interested in the case where we're less than or equal to 0. Well, we're less than 0 here and greater than 0 here. So this checks, whereas that doesn't. This test number checks as a location where we're less than 0. This test number doesn't. So here with our boundary of 3, where we're not allowed to be equal to 0, right, or where we have our domain concern, or we're just simply not allowed to be a value of x, our test number is 0 says that our solution must be everything less than the value of 3. Right? And overall as an interval, that is from negative infinity up to the value of 3, not including the value of 3. Keep in mind we can always check this answer, folks. If I was to go over to my calculator here, put in this function, I'll put the numerator in parentheses, and I'm going to drop the denominator in parentheses here. All right, that's one way to make sure that you have it treat the numerator as the numerator and the denominator as the denominator to avoid confusing our calculator. Then if I just look at the graph, certainly here I'm still out of zoom. I'm going to go over and zoom standard. That goes back to your normal settings here, right? And you can certainly see in our graph right there at 3 is where we have this domain concern. We have this vertical asymptote happening in our graph, right? That does divide where we see two different types of behavior in this function. One type of behavior where we're below the x-axis, this situation here, and the other type of behavior where we're above the x-axis, this behavior here. Remember, when we're below the x-axis, we're less than 0, and when we're above the x-axis, we're greater than 0. So here we are less than 0, which is what we're interested in our example here, for all the values of x, all the way down to negative infinity, up to this domain concern at the value of 3. All right? So our graph should check with our solutions here, right? Our algebraic methods, right? And again here, with rationals, you do want to treat it a bit like an equation to begin with, which you want to think about where you have your domain concerns and where you're going to have your solutions. Locate your domain concerns and your solutions along your number line, and then pick numbers between those bounds as test numbers, and test those numbers for the condition you're seeking in your inequality. Here we're seeking less than 0, so this is the case where my test number of x equal to 0 causes that behavior. Well, 0's in this interval, right? In this interval less than this boundary of 3, so this interval here where we're less than 3 must be our solution to that inequality. And all that is supported graphically, right? Folks, I'll be back with another quick example in just a moment. All right, College Algebra back with another quick example of solving a rational inequality. We see here on the left-hand side of this inequality symbol, we have the difference of two rational arguments, right? And in fact, you could think of these as one rational function by itself over there on the left-hand side. If we actually bring this down, one of the ways we could start to think about this quantity over here on the left-hand side, and as I highlight, we often think of this as being set equal to that value of 0 to begin with, where what we have all by itself over here on this left-hand side is what we think of as being the function f of x, right? Which we can form into a little bit more of an explicit rational function by combining these over a common denominator. In fact, I might consider doing that, our common denominator being the denominator seen here and the denominator seen here. So this would be x minus 2 times an x minus 1. Were to obtain a common denominator in this first term, I would have to multiply both the top and the bottom by this portion given by x minus 1, that factor. So that would be x plus 1 times x minus 1. And that would be all minus what I would get to obtain a common denominator here in this term, where we would need this portion given by x minus 2, this factor x minus 2. Multiplying the top and the bottom by x minus 2 will produce that common denominator. So that would be x minus 3 times an x minus 2. And all that must equal 0. All right? We could begin here, but let's clean up this numerator. I think a little bit might be helpful, so we might go a little further with this. In the denominator, let's go ahead and leave that factored. That's going to be useful to us factored. Right? But up here in our numerator, x plus 1 times x minus 1, if we expand that out, that is x squared minus 1. right? That is a special binomial product. That is an a plus b times an a minus b form, so that's a squared minus b squared. We get that result here. Minus what we would have here. Now, this is going to expand to become its own quantity. That would be x times x is x squared. We would have minus 3x minus 2x in the middle there, so negative 3 minus 2 is negative 5x. Right? And then at the end, we would have the constant given by negative 3 times negative 2, which is plus 6. Right? Now, a big mistake a lot of students are still making this semester is this negative does have to always distribute across a group, right? You do have to distribute your negative factors here. I see a lot of students just drop the parentheses and forget that distribute. Don't do that. If we leave the denominator alone, that's going to be useful to us as a factored form. But here in the numerator, we're going to have an x squared minus 1 minus an x squared. Distributing the negative, we get plus 5x. Distributing the negative, we would have a minus 6 in value. Where we can certainly clean up this numerator a little bit, and we should see that that numerator, right, the x squared minus the x squared cancel, right, and what we're left with here is the quantity 5x minus 7. Minus 7 coming from negative 1 minus 6. That's minus 7 all over x minus 2 times x minus 1 in value. And all that equal to 0. So if we think about that rational function that we started with on the left-hand side, this function f of x, it can actually be expressed as this, a little bit more of a familiar form, by doing a little bit of combining these two terms with a common denominator. All right. We are going to now approach it the same way we were going to approach it up here, as treating it like an equation to begin solving this inequality. So let me bring over another sheet here. What we do know up above. All right, folks, I'm back. Sorry I got interrupted there. Again, keep in mind what we had done just in our previous, in the beginnings of Part B here, is we did rewrite this rational argument found on the left-hand side of this inequality into this specific rational function given here. So what we really are facing now is solving this, right? The problem, in a sense, gets translated into solve this inequality, right? We're to begin solving that inequality, we are going to want to think about it, again, a bit like an equation, as this function f of x on the left, 5x minus 7 over x minus 2 times x minus 1. Think of it as this function on the left, where we're interested in the values where x equals 0. To begin finding where we're less than or greater than a value like 0, we do want to consider where we equal 0 in that inequality, right? Now, for f of x being a rational form, there are, again, values of x you're not allowed to be, and those are your domain concerns. So if we start there, we would note, right, x minus 2 times x minus 1 in our domain, right, or as values in our denominator, are not allowed to be 0, right? That product is not allowed to be 0, which means x minus 2 cannot equal 0, or x cannot be 2. X minus 1 cannot equal 0, or x is not allowed to be the value of 1, right? So right away, when we think about values of x, right, as being either solutions to this equation or this inequality, they are not allowed to be the value of 1 or the value of 2, right? These values of x must be excluded from any answer, and these values, or this value of x, must be excluded from any answer, right? To begin with, we know that from our domain concerns. Now, as for when f of x equals 0, right, we might note f of x equals 0 when what's true? Well, that's when this numerator, 5x minus 7 equals 0, or that's when 5x equals 7 or x equals 7/5 in value. Now, what is 7/5 in value? That is 1 2/5, or what we understand as the decimal 1.4 in value. Now, this is what happens sometimes with rational situations. Everything kind of gets squeezed into this one little region along our number line here. So right here, 1.4 is right there. That would maybe be our location for 7/5, 1.4. That is where we equal 0. But if we go back to our inequality, we're actually interested in where are we less than 0. So this is where we equal 0. This also is not going to be allowed to be a solution in our inequality. Right? If we actually blow up our number line a little bit here, right? Here we might have 0. Here we have 1. Let's make that a little larger, right? Here we have 1. Here we have 2. Right? Here's 1. Here's 2. We also found 7/5 right about here. Right? We're not allowed to be here, here, or here along our number line for x. Right? So what we do now is we're going to pick some test numbers that lie within these bounds, right? And plug them into our function f of x and see when we satisfy this condition. Some good test numbers, we maybe would pick 0, right? 0's out there, that's a good test number. We might test the number between 1 and 7/5. Well, 7/5 again this is 1.4. So maybe we test 1.25. We can test a decimal if we like. So we'll go ahead and test 1.25. Again, between 1.4 and 2, maybe we could test 1.5. 1.5 would fall within that interval. And then certainly we want to test greater than 2. Maybe we test the value of 3. Right? Again, where we test these values at is on our calculator. If we go underneath our y equals menu, you can see I've already put this into my calculator. I do want to notice I grouped my numerator in a group of parentheses and divided that by my denominator here in a group of parentheses, where the denominator also has those two factors, x minus 2 and x minus 1, each in their own set of parentheses. All right? If I now go over to the table, let me delete this out. Let's run these test numbers. If I test 0, I get negative 3.5. If I test 1.25, now you can see where the calculator comes in nice for testing these decimals. Ooh, I get the value of 4. If I test 1.5, I get the value of negative 2. And if I test the value of 3, I get the value of 4. And again, we're interested in where are we less than 0? Well, we're less than 0 here, greater than 0 here, less than 0 here, and greater than 0 here, right? Anywhere we're greater than 0 is not what we're interested in. These two cases get cut away, and here are the values of x that lie within the intervals where our output, f of x, is less than 0. Right? So what is that? That is this interval out here, all the way down to negative infinity, right? This is from negative infinity up to this boundary at 1, unioned with, right, this interval that includes the 1.5. That's this little region of space right in here, right? That is from 7/5 up to the value of 2, and we don't include either of those boundaries, right? Now notice we should be able to see this also graphically. If we go back over and look at the graph here, right? We do see, and maybe we should zoom in here. Let me zoom in to right about here. Right between 1 and 2 might be a good place to kind of zoom in. Let's see if we can see some of our picture here. Let's do this. Let's change our window settings. Let's go back to standard zoom. Apparently it's going to crash. So let me go back to my graph. There we go. Getting that standard zoom here. All right. And then let's adjust our window settings. Let's look between here and here, right? Let's maybe make our x's between maybe a -3 and a +3 in value. And then maybe we'll leave the y's where they're at. So we'll zoom in a little bit here. So x is between -3 and maybe we zoom into 3 in value. But let's leave the y's where they're at. Let's see what kind of picture we get. There we go. A little clearer, right? Where we can see kind of a little bit more of what's going on here. But we definitely see these two boundaries. Again, go back to the problem. We had these two boundaries caused, or these vertical asymptotes caused by our domain concerns. At x couldn't be 2 and x couldn't be the value of 1. We see that happening here in our graph. We would expect these vertical asymptotes at 1 and at the value of 2. Right? We also are interested in where our function equals 0 to begin finding where it's less than 0. So where it equals 0 is actually right there on our graph, between 1 and 2 at about the halfway mark, which was 1.4 in value. Right? With those boundaries established, we had established them at 1, 7/5, and 2, we can then see where are we less than 0, where are we below the x-axis. We are below the x-axis for everything here to the left of this boundary at 1, right? Which is what this says here in our graph, right? And we are less than 0 below the x-axis, right? Starting at this 1.4 and coming up to this vertical asymptote here at 2. That is this region described between 7/5 and 2. Between these other bounds, we're above, right? We're above up here and we're above there, the x-axis. That is where we happen to be greater than 0 in this case. Right? So folks, in this particular scenario, keep in mind it all began by rewriting our left-hand side to get a little bit more familiar of a rational form. And then when solving a rational inequality, or even the case for an equation, you want to keep in mind, first of all, what are your domain concerns? Because you're not allowed to have any x's be these values. So these cannot be included in your inequalities. Right? And then you want to look at where does that rational function actually equal 0, which involves, as we've noted, analyzing your numerator. When does that happen to equal 0? Right? We do that over here. Once we find these places we can't be for x and this boundary where we equal 0, we lay these out on our number line. We pick some test numbers within those bounds. We test those values, and at times you are going to have to work with decimals. And that test happens really conveniently here underneath the table feature of our calculator. All right? Where based upon the results of the test, we are looking for the case where we're less than 0, which is in this scenario and this scenario for x, where x equals 0 and 1.5, which corresponds to these regions. And in the end, when you get your final answer, you should be able to go back to your graph on your calculator and see that all that correlates with our graph. Where we're less than 0 is where we're below this x-axis. Well, that's from -infinity up to this boundary at 1. And then starting where we equal 0, right there at 7/5 up to this boundary at 2. Those are the locations where we're below the x-axis. Right? All described here by these intervals. All right. So folks, that was another quick example of solving rational inequalities. I got one more for you. I will come back and look at that one in just a moment. All right, college algebra folks, one last quick example looking here at solving a rational inequality. In this particular case, we do have this rational inequality on the left being greater than this rational inequality on the right of this inequality statement. Now, the way that I would approach this, again, is very similar to how we worked through the previous problem and problems, is I would consider producing a 0 on one side of this inequality. One way we could produce that 0 without having to really rearrange this inequality symbol is to subtract one of these sides from the other. So maybe we consider subtracting this value on the right-hand side from both sides and moving it to the left-hand side. If I do that, I will produce this result here, right? 2 over x squared plus 3 minus 3 over 5 plus 4x squared, right? And all of that, when you add and subtract on both sides of an inequality, it does not change the direction of the inequality symbol, folks. You want to be very careful using multiplication and division when moving variable values of x from one side to the other, because if that value of x has a potential of being negative, it could switch the direction of your sign, right? Once on this left-hand side, we might do what we did in the previous case, right, where we consider combining these over a common denominator. On the left-hand side, that common denominator would just be the denominator of the first rational argument times the denominator here of our second rational argument. That would produce our common denominator. Now, once that common denominator is produced, we now need to rewrite our numerator. This term, to have that common denominator, does need to be multiplied by this factor 5 plus 4x squared. So 2 will be multiplied by 5 plus 4x squared. And this value minus 3 has to be multiplied by this denominator to produce this common denominator. That would be the quantity x squared plus 3. So if we simplify, or I should really say expand this numerator and simplify, all right, I am going to leave my denominator alone in its nice and factored form, and I actually might rearrange this last factor to give me a nice descending format for the degrees of the polynomial. But up here in the numerator, I would distribute my 2 through the first term. That would produce 10 plus 8x squared. I would have to distribute a minus 3 through the factor here, x squared plus 3. That would produce negative 3x squared minus 9. And then lastly, I would consider simplifying this numerator. Again, I'm going to leave this denominator alone. All right? And to simplify the numerator, I would say 8x squared minus 3x squared. Well, that is 5x squared. And 10 minus 9, well, that is plus 1 in value. All right? So as we go to solve this, we are going to look at, right, to begin with, well, so what do we have here? We have essentially this inequality statement expressed now in terms of, right, this argument here, right? We've transformed it into this explicit rational function. We might say this is our explicit rational function now, all right? So let's maybe give ourselves a little bit more room and bring that up here, right? So we now are really being asked to solve, where is 5x squared plus 1 all over x squared plus 3 times 4x squared plus 5 greater than 0. All right? And keep in mind where we begin then is we start with this domain, right? And we might ask ourselves, note, x squared plus 3 times 4x squared plus 5 is not allowed to be 0. We have to exclude these values of x that might cause either one of these factors to equal 0. Now, note here, that means x squared plus 3 cannot equal 0, or 4x squared plus 5 cannot equal 0. Well, in this case, this would imply that x squared would not be able to be negative 3 in value. Which, one thing we point out, this never occurs. This is no real value. This has no solution, or what we say is no real solution. It does have an imaginary. X does equal what we might say is plus or minus the square root of 3i. It is an imaginary solution, but this is not going to be a location along our number line for x. Right? We really see there's no real solution from this scenario. Similarly, if we work through that over here, subtract the 5 from both sides and divide by 4, we find x squared is going to be negative 5/4, or cannot be negative 5/4 in value. Well, that also has no real solution. Again, you would encounter an imaginary solution there. Right? X would equal plus or minus the square root of 5 over 2i if we went to go find that solution, but this is going to lead to no value on our number line where we can't be that value of x. Right? There's no real solution where that happens to occur at. So our denominator does not really bring up any domain concerns. It still says that you can be any value of x you want to be along this number line. Right? No domain concerns, in a sense. Your domain can be anything from negative up to positive infinity. Next, we note, if we think of this as function f of x, right, we consider when does it equal 0. Right? We might note f of x equals 0 when what's true? Remember, that's where we look to our numerator. That's where 5x squared plus 1 equals 0. And you might see something similar to what you saw down here, right? As we go to solve for x in this case, you end up with x squared equals negative 1/5 in value, which again we'll note has no real solution. Right? There's no real solution that causes x to actually equal 0. So we find no values along this number line that would be a boundary between when this argument is greater than 0 or when this argument here for f of x is less than 0. There are no boundaries. Right? In a sense, the only boundaries are negative and positive infinity. Those are the only boundaries we have on what could be a potential solution. To determine our solution, and our solution could be one of two things here now, it could either be from negative to positive infinity, this being the only interval in which we will see it being either greater than 0 or less than 0, or it'll be no solution. Right? There'll be nowhere along here where this happens to be greater than 0. How do we determine what's going on? We choose a test number. So maybe we test the number as 0. If we notice, plugging in 0 into our function, we're interested in, does it make it bigger than 0? Right? And it doesn't take much to plug in 0 here. Notice 0 plugged into the numerator, 0 squared is 0 times 5 is 0 plus 1 is 1 in the numerator. Over, plugging in a 0 in the denominator here, produces 3 times 5, which is 15 in value. Right? So this, when 0 is substituted into f of x, it does result in a 1/15 in value, which is bigger than 0. So this must lie in an interval where we are bigger than 0. The solution here must be this entire interval, starting all the way down here at negative infinity and continuing all the way up here to the case for positive infinity. This must be our solution. Now we can check that. We could go underneath our calculator here Let's set our zoom setting back to standard. Let's go underneath our graph here. And in case you don't believe me, we can actually go back and actually plug in this statement here if we wanted into our calculator. This might be a little easier to put in. You could put in 2 divided by x squared plus 3 as a quantity minus 3 divided by the quantity 5 plus 4x squared. Right? Where now if we hit the graph button, we should see our graph appear. And it is there. It's a little hard to see. What we do notice is that at 0, it is 1/15 in value. It is very, 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 very small in value. So what we might do here to see our graph a little bit more clearly, let's zoom in a little bit. All right? Let's zoom in to maybe, let's go to -5 to 5 to begin with for x. Well, actually, let's leave those alone. Let's go from -10 to 10. We'll leave those alone. Let's zoom in here. Let's go from -1 to 1 for y. Let's zoom in along that y-axis. Ooh, and we can kind of see that graph appearing now, right? It does run along the x-axis. It appears that it's always above, and that is implied by our solution here, right? Where what we note is if we're interested in where are we bigger than 0, where we're bigger than 0 is everywhere above this x-axis. And this graph appears to run along the x-axis, always being above it. Everywhere from negative to positive infinity, this graph appears to be above that x-axis, right? So it does correlate with what we find to be the solution to this rational inequality, right? So folks, again, solving a rational inequality, usually the best approach is to get 0 on one side, right? We know how to analyze equations when they're set equal to 0, and we were doing that here, right? To get 0 on one side, best bet is to either add or subtract the terms on one side to the other, which we did here. We subtracted the right to the left. Combine them, right, using a common denominator, and produce this one rational argument that you're now going to analyze with respect to 0. You are going to want to watch out for your domain concerns, and in some cases you're not going to have any domain concerns. So there'll be no regions along the x-axis where you're concerned about domain, right, and not allowed to be at those locations. Here we're allowed to be anything from negative to positive infinity. And then you concern yourself, if you're interested in where you're greater than or less than 0, is where your function equals 0, which is pretty easy to determine by just looking at when this numerator equals 0. And again, a lot like in this case, we can see at times there's also no real solution that might appear there. Which means if you have no boundaries other than negative and positive infinity on your possible solutions to this inequality, right, your answer is either going to be that entire interval from negative to positive infinity, or the other thing that could have happened would have been no solution, or no solution in value. If this would have been negative 1/15 in this example, and we were less than 0, we would have said we had no solution. And in the end, your answer should correlate with your picture. Where if you're comparing to 0, is done with the x-axis. You're greater than 0 when you're above it, you're less than 0 when you're below it. And this graph does correlate with our solution that's seen down here, folks. All right? So, again, folks, that's solving polynomial and rational inequalities. Hope that helps, and I will be back in the next video looking at some examples from section 5.1 material. We're moving up into chapter 5. See y'all then.